Good morning, everybody. Today we have a Codeforces round. It's a Div 3 round, and it's round 710. So I'm excited. It's been a while since I made a video, so yeah, we'll have some fun here. We'll jump right into that, but a few announcements before we start. So this weekend is CodeJam qualification round, so don't forget about that, because if you do, then you can't compete in the more challenging CodeJam rounds. The qualification round shouldn't be too bad. Really, more than anything, it's kind of like a mandatory practice than an actual contest. So it's just like, don't forget to do it. Yeah. Then we have this Div 3 round, which will be something fun to do today. And let's start with deleting our old classes, and then we can jump in. We're also still in the process of our switch to Kotlin experiment. We're seeing how that works. And if that winds up being fun, then yeah, there we go. Then we'll do that long term. Also, since it's a Div 3 round, I'm going to prioritize explaining what I'm doing rather than just like performing well, which is part of the reason why I'm totally fine starting 6 minutes late. So here we go. In problem A, Polycarp is a rectangular table of n rows and m columns. You notice that each cell in the table has a number. Excuse me, a number. Man, I can't say the word number today. Voice crack every time I say it. Obtained by the following algorithm by columns. Yeah, okay, gotcha. Then you've got by rows. Doesn't have much time, so he asks you to find the cell number and by rows. I see. So yeah, we just find the row column and then we can work back. Alright, so what are we looking for here? Zoom in so you guys can see. So we want the height, width, and x. So val, I guess let's just call this n. So x will be, or let's make these variables n minus minus, because that way we have it 0 indexed, and then we'll say val x equals, so the x coordinate is n divided by the height, and then the y coordinate is n mod the height. Okay, and then the ants will be, if we go by rows instead, it'll be x plus y times width, and then plus 1. Cool. So that's problem A. Let's see if that's correct. Oh, okay, yeah, so it needs to be long. Not even close. Interesting. Where does 15,000 come from? Oh, read line dot split on a space dot map. Yeah. That would do it. Okay. So submit to problem A in Kotlin. Everyone's probably looking at me thinking like, how can you not read this column here? All right, cool. So there's Kotlin. Problem A. Good, good, very good. All right, problem B, partial replacement. You're given, we got it, awesome. given a number k and a string s of length n of dots and asterisks. Place some of the asterisks with x's so the following conditions are met. The first asterisk is replaced, the last one is replaced. The distance between two neighboring replaced characters must not exceed x. Gotcha. So must not exceed 3. So there, there, and then the last one. Yeah. So that's a good question, actually. It's not super obvious. So let's think about it for a moment here. So if we've got some string, so this needs to be an x, and this first one needs to be an x. So the distance between two neighboring asterisks is too big. So if we have like this case, yeah, so okay, so if the distance is too big, like between maybe this first one and this last one, for instance, we have to replace one of the two. If we assume the prefix is solved, we always want to replace this last one, right? Because the last one might affect future things, but this first one will only affect things we already have figured out. So every time we come across a situation, we'll always, oh wait, that's not the case. Because like, then we have this, so we would have to replace this entire suffix. So if we had something like this, then, yeah, then we would want, like you have to either replace these first two or these last three. So, gotcha. So you'd want to replace the first two. So you just need to find some continuous range of asterisks. That's the solution. Okay, cool. Should be pretty easy to implement, I think. So we want n, and what's the second number? K. Oh yeah, K, the distance. So this would be read line dot split on a space dot map to an int. Okay, so val line equals read line dot array. Actually, we don't even need to do this in Kotlin because we have array accesses, which is pretty nice. So we want var first index can I do line dot first? Oh my goodness, so nice. That's the nicest thing ever. Look at that. This is so clean. Okay. And then we can make a last index is line dot index of last. Good, good. So now we just see, isn't Kotlin fantastic? You just feel so happy when you use it. Now we just need the, let's get some more room here. We just need the cumulative sum array. Oh, we can just do 0 dot dot n. It's kind of clean. All right. So good. All right, so that's our prefix sums. We've got that. And now we just need to find all of the possible places that we can use this. So val max skipped. Oh, we also need the count. Okay, so that's how many stars there are. We want to var max keep equals 0, and then finally print line max keep minus count. All right, so now how do we calculate this max keep? So for I in 0 until n, so this is the start, I guess this can be L. R will be L plus K minus 1. So we're going to keep this range of stars. Yeah. So this is going to be, I guess, the min of this and last index minus 1, because the last index has to be an x, so we can't use that. And we can just make this first index plus 1. So guaranteed this has a well, we'll just special case this. How about that? So if I'm in the repeat thing. Okay, it's kind of annoying you can't continue outside of a like repeat loop, but anyway. Okay, and then finally max keep equals max keep, and then prefix sums at R plus 1 minus prefix sums at L. Minus 3, interesting. Why is this the case? There's a good break case. Yeah, okay, so first index, last index. We start at first index plus 1. The R is whichever is smaller, L plus 1. Or this. Yeah, alright, so why are we wrong? Interesting. Alright, I really need to start doing the Control-Shift F10, don't I? Okay. You're telling me I need to replace all three of these for it to be the case. This is between any two neighboring X characters. Oh, I'm doing the wrong problem. I was solving the problem of the distance between any two neighboring asterisks must not exceed k. And they have to be neighboring. Okay, so back to the drawing board. The idea here is just if you have this, what you need to do is simply, if you exceed k, you replace this with an x. Yeah, okay. All right, so let's try this again. We don't need to special case this. I guess if count's equal to 0, then we do. Otherwise, we have the first index to the last index. We don't need prefix sums. We do need an answer. Okay, so then we can just go from first index until last index. So to do that, we just, yeah, okay, so if line L is not equal to an asterisk, then continue. If it is, if the distance between us and the last time we marked something is too big, then count plus plus and last star equals last. So like, yeah, if the gap is too big, then the last thing we marked as a period needs to be an asterisk, or as an asterisk needs to be an X. It's used right here. What do you mean? It's not true. It sure is. It's used right here. Oh, right here. Gotcha. So this is oh, this is the last. Yeah, okay. Then last equals last star. So this is the last X, this is the last star. Yeah. Yeah, okay. That was a very easy problem. I have no idea why it took me so long. The main reason was because I misread it, I think. Good, good. Now, yeah, okay. So, this is when we need to convert it. Okay, the other cases are when we're the first or the last index. All right, so interestingly, we also fail this case here. No more than K. It's taking me a long time. Why is this the case? All right, so yeah, this is wrong, I think. Wait, no, it's not. Ah. Control Shift F10 to run. Okay, it does work. It's just very leggy. And then we want to run just one case of this. Oops. So there's one case in which we don't do it. L is 0. Oh, L is 2. Last X is 0. So 2 minus 0 is greater than K. Oh, yeah. So this case is to increment the last thing, but we also need a different case. So three, one. Okay, so we still don't print it. And I guess this is for this here. It's not an else if, it's just an if. Good. All right. So this has been a very messy problem D with David. Problem B, what am I saying? Ooh, beyond me how that took 20 minutes. That's very embarrassing. Anyway, keep going. We'll hear a result soon. You're given strings A and B of lowercase Latin letters. You can do the following any number of times in any order. If A is greater than 0, delete the first character of A and replace A with that. So you can just delete the first character, you can delete the last character, delete the first character of B, delete the last character of B. Note that after each of the operations, A or B may become empty. So you want to make the two strings equal. So yeah, you're going to delete some characters from each. You want to see what's the longest common substring. So in this case, the answer is 2. Oh, AA, 0. This is 2. This, it's just the E, I think. So it's 4 for the H, and then nine. 4 plus 9 is 13. Yeah, pretty easy. Okay, so let's do that real quick. Good. Okay, for I in 0 until SA dot length, for J in 0 until SB dot length, for K in math dot min, IJ, wait, nope, never mind. K in 0 until math.min of SA.length minus I, SB.length minus J. All right, so we have each of these things. What else do we need? We just need to check if they're not equal. If they're not equal, then break. So var max match equals 0, and then print line SA.length plus SB.length minus 2 times max match. If SA at I plus K is not equal to SB at J plus K, then break. Otherwise, max match equals max.max match for K. Plus 1. Good, that's problem C. Moving on to problem D. Epic transformation. You're given an array of n integers. You can apply the operation consisting of several steps, 0 or more times. Select two different numbers in the array. Remove the ith and jth elements from the array. Oh, you can remove two numbers if they're different. Output the minimum possible size of the array after applying some sequence of operations to it. So we want to know the count of the max element. Sounds good. All right. So we have the test cases. Val n equals read line dot to int. Val a equals read line dot split on a space dot map it dot to int. All right, and we need a count. So how big can these things be? Pretty big. Do you want to do coordinate compression? That'd be kind of annoying. Let's do a map. So for I, well, okay, a dot for each map at it dot increment. Can we do that? It would be, okay, if I were writing Kotlin, what is this doing? Okay, there's put if absent, remove, I want like an increment if it doesn't exist. I can do this in 2 lines very easily, but it would be super nice if this was already a thing that exists. What does compute do? Oh, maybe it like computes the sum or something. Okay, I guess this is just going to be dumb. So if not map that contains it map it equals 0. Map it plus plus. Seems like a really ugly way of doing stuff. For Kotlin, usually things are clean. Anyway, map all right, sure, that works. Okay, what's the what was I doing here back before I started programming this? Counting which one occurs the max. All right, cool. So we have that. That all works out. Now we just need to print the answer. Yeah, so print line math.max of n modulo 2 n minus 2 times the max count. Oh, 2 times really n minus the max count. Because that's how many things aren't the max. Yeah. So, okay, what do these do? This first part says the parity. If the parity is even, the answer has to be at least 0. If the parity is odd, it has to be at least 1. This number here is how many things aren't equal to the max, whichever thing occurs the most. You can only delete once for each of those. So if there's like only one thing that isn't a 3, you can only do one deletion. Or that's what this number is. So you delete 2 numbers for each of those, and then n minus that is how many's left over. Is that epic? I don't know. I feel like that's lacking in the epic department, perhaps. Permutation is a sequence of n integers from 1 to n where each number occurs once. Polycarp was presented with a permutation of numbers from 1 to n. When Polycarp came home, he noticed in his pocket the permutation had turned into an array according to the following rule. Each element is the max of its prefix. Now Polycarp wondered what is the lexicographically minimal and lexicographically maximal permutations which could be presented to him. So yeah. So in this case, you have like 3, 2, 4. Is it possible? Yeah, okay, so it's guaranteed to be possible. So you have like, the minimum would be 3, or the maximum would be 3, 2, 4, 1, 7, 6, 5. Yeah. Yeah, okay, it's easy. We can just do this with the priority queue. E. So yes, the idea is just like, I mean, you just do it greedily from front to back. Good, and then we want the answer here. So we need val min ans equals int array of size n. All right. So val pq min equals priority queue int. Oh, I guess just compare by. Pretty clean, to be honest. Okay, how do you, in Kotlin, this is not actually part of the contest, I just want to learn how to do this. If you have two things, oh, that's kind of ugly. That's really ugly. Oh man, what is going on here? Companion object. So you pass in this custom comparator. I've never even seen this before. There's some crazy nonsense going on here. When? I'm getting very distracted. But what is going on? It's a switch case, but you can do anything in it? Oh my goodness. Whoa. Whoa. That is so cool. Learn something new every day. That's what I've learned today. Nothing to do with competitive programming, but that's a cool thing to learn, I think. What were we doing? Yeah, good. All right, we have this. Very cool. PQ min, PQ max. Okay, so val max scene, or this is a variable, equals 0 for I in range from 0 until n. We're not typing Python here. Okay, so for to add in range 0 until, I guess we just do while max scene is less than 8i. Max scene plus plus, and then PQ min dot add max scene, PQ max dot add max scene. Cool. So we have this. So now we have the two things, and now we say min ansat I equals PQ min dot remove. PQ max dot remove. Okay, so Boolean bool max scene is not equal to 8i. So if we are new, then min ansat I equals 8i, max ansat I equals 8i. Yeah, that should be good. Oh, and then finally print line min ans dot to string, join a string, space, and then max answer to do the same thing. Recompiling. Come on, this should be building faster. What's going on here? Control Shift F10. Three 14275 324 1765 1234. Looks good. All right. Well, interesting that this has fewer solves. We might as well just read this first then. Yeah, we got it. All right. You're given a string of lowercase letters. Well, there is at least one character in the string that is repeated at least, wait, what? Well, there's at least one character that's repeated at least twice. You can perform the following operation. Choose one index such that the character at position I occurs at least 2 times in S, and delete the character in position I. So you delete one thing that occurs twice. Given a string S, find the lexicographically maximum string that can be obtained after a certain sequence of operations in which all characters in the string become unique. So C okay. So we look at the smallest character in the array. The last occurrence of it we have to keep where it is. Well, okay, let's look at it differently. The biggest character in the array, we want to keep the first occurrence of it. Yeah, that's not really helpful. So instead, we look at the first character we keep, we want it to be as big as possible. So can the first character be the biggest character, can the first character be Z? So you look at, can you not take anything, then take a Z, and then take everything after the Z? Does that have the same set of characters included? Yeah, so we can do this in, well, it's going to be 26 squared times 2 to the 5th. Yeah, I guess we can try that. Might not hurt. This will return some int. So it returns a bit mask of things we use. All right, so var c equals false for, I guess we just start for each. If scene equals take first, then scene equals true. Oh, if it equals take first, scene equals true. Scene res or equals 1 left shift it minus a. Hello? Are you serious? What? No way. No, what? Or, that is wild. this is kind of wacky. 1 SHL. Shift left. That's kind of wacky. Alright. So res or 1 left shift that. Gotcha. Return res. Yeah, okay. So that's what happens if we get something that's used. There ants equals this. Print line ants. Okay, so var all chars equals get used. Well, what do we need here? So, yeah. So okay. Val the string is read the line. So this is like the entire string. All characters, this will be an int, which is if we have the entire string and we take the first character, what does it look like? So now for I in Z down to A, if get used s, this is going to be a variable actually. If get used s, we first take now equals all chars, then ants plus equals take now. First index will be s dot first, or index of first. So now we need to delete the first prefix. Substring at first index, and then s equals s dot replace all. There's got to be a clean way of doing this. I mean, I could definitely just write code that works, but the div3 round, right? Oh, so you can just call that to, well, that's to regex. Oh, so this needs to be dot to string. Oh, cool. Yeah, so we take the substring of the first index, and then we replace everything after. Good. Is it that easy? Nope. Not even close. Okay. Oh, yeah. Okay, so now we have to remove this from, like, the list of all characters. One left shift by, or shift left by take now minus A. Really? Oh, because you can't ever increase. Yeah. Oh, that's so annoying. Okay. Okay, what's going on here? Good. All right, let's submit this. My Niak. Yep, that's good. Consider an infinite triangle made up of layers. Let's number the layers, starting from 1, from the top of the triangle, top to bottom. The kth layer consists of k points, numbered left to right. Each point of an infinite triangle is described by a pair of numbers, where r is the number of the layer and c is the point on the layer. Okay, I think. What's the problem? The minimum cost of a path associated. This is very confusing. Okay. From each point RC, there are two directed edges to the point. Okay, I think I see. If it's even, then the edge is activated. Otherwise, the edge is not activated. Okay, this is, I don't like this problem. It's very hard to read. Each point is an infinite triangle. Oh, each point of an infinite triangle is a pair of numbers. So this is the layer, C is the place in the layer. From each point, there are two directed edges, R plus 1C, C plus 1, yep. But only one of the edges is activated. If this is even, then if it's even, this one's or if it's even, you go left. If it's odd, you go right. Okay. From the point, it's possible to reach the point R2 if there is a path on activated edges. Initially, you're at 1, 1. You can replace the activated edge. Yes, you can switch it, or you can move. You're given a sequence of n points on the infinite triangle. Find the minimum cost from 1, 1, passing through all endpoints in arbitrary order. Can you go back up? Okay. Okay. So 1, 1 to 4, 3, 2, 1. They give us 10 to the 5th numbers, each up to 10 to the 9. Ugh. Oh, it's disgusting. Oh wait, this does not increase the cost of the path. So the number of turns doesn't matter. Yeah, okay, so I guess we need to go draw out some cases. That's how this works. All right. So we have 1, 1, then we have 2, 1, 3, 1, 4, 1. 2, 3, 2, 3, 3, 4, 2, 4, 3, 4, 4. So initially it's even, so it goes left, right? Yeah, so this is even. This goes right, left. Then this is even. This is odd, so it goes right, that. I see. Okay, so they're saying you need to go from 1, 1 to 4, 3. So 1, 1, 4, 3. Two, 1. Okay, gotcha. So that's all in one path. So no changes required. Presumably you can go up. Do you ever need to go up? No, you can't always go up. Because if they said, yeah, are these directed edges? They are directed edges, so you can't go up. Okay. Gotcha. So that means each of the... So if we sort these by the first number, then we have the order that we need to traverse them in. Yeah. So either... Yeah, okay, so like if you're at this height where the height is odd, so if it's odd, then you can go down and then go right for, you can go right for free as many times as you'd like. But if it's even, going right costs 1. So it's just kind of messy, but it's pretty straightforward, I think. It's just very caseworky. I think this is ultimately just like a bad problem. It's like a classic not interesting problem. So, am I not allowed to do this? Size 0. What's wrong? That is like super ugly code. Okay, anyway. Add, dot append. Okay, read line dot, oh my goodness, this isn't gonna work. Okay, so val rows equals read line dot split on space dot map it dot to int. Okay, so that's the rows. We also have the columns. For I in range, or I in 0 till n, pairs dot add list or int array of rows at I, columns at I. Is that a thing I can do? All right. Pairs dot sort by it dot or it at 0. This is kind of ridiculous. You're really going to give me the same thing multiple times? Really? That's so lame. Okay, anyway. Okay, so pairs dot add 1 1. So we've got, we want to go from this to this. Good. So now we just need to do this and then write the method. Okay, so var count equals 0, 0l, or I guess just 0 should be fine. Print line count for I in 0 until pairs dot length or dot size minus 1. Count plus equals go from, can we start anywhere, or do we have to start, you start at 1 1, okay. Go from pairs at I 0, pairs at I 1, pairs at I plus 1 0, pairs at I plus 1 to 1. All right, if from R is the same as to R, that means we don't actually move, so we can return 0. Otherwise, we just care about whether, or we care about the difference and also whether we start on an even. So if, well, okay, so val dr equals 2r minus from r. Yeah, so if from r mod 2 equals 0, we do one thing, otherwise we do another. So, adding is free. Going left costs 1. So val target C will be from C plus dr. So then we want to return target C minus 2C. That's how many times we need to move left. Oh, that's not the case, because the first move left costs 1, but the next one is free. Plus 1 over 2. Okay, going left twice costs 1. Gotcha. Okay, otherwise, so we can either, yeah, so okay, if we need to go right the entire time, we can do that. Or if we don't, we might as well go left now. So if then return, then every turn we have to switch. So this is return dr. Otherwise, return go from r plus 1. Which column? Same column, same target. Okay, we got the second case wrong. 2-3 to 2-4. So we start here, then we have, there is no 2-3. Is the first thing the column? Oh, 2-2, 2-2, 4-3, 4-3. So there's a cost of 1. So this first one does cost 1, but then 2-2 to 4-3 should not. Yeah, because I'm considering only the first element rather than the first plus the second. Okay, so this is not from R, this is from R plus from C. I think I have this backwards now. It's not equal to 0. And then this is a bit confusing, but 2, 9, 9, 9. Okay, 0, 1, 9, 9, 9, and then a 2. Looks good. All right, so I think that's the contest. I guess F wasn't terrible. I didn't really enjoy it. That was a very slow Div 3 for me, though. Yeah, we're probably in like 1000th place here. 100th place, still quite bad. Anyway. Yeah. Well, yeah. Oh, hey, look, my brother's doing it. Is it good? Who's my brother? Spoiler alert. Yeah. So there you go. There's the contest. I guess we'll go over solutions real quick. It'll be very brief because problems are pretty easy, but I'll just kind of briefly explain them. So for problem A, you have like two grids. One grid is like by column, and the other grid is by row. And you want to say for some number, if it's this number in if it's this number in by row, what is it in by column? Nope, vice versa. If it's this number by column, what would it be in by row? So the idea here is that you just need to like be able to convert both ways, and you can do this with modular division and regular division. So for each column, right, you know, after a full loop through the column, the number will increase by the height. So if you zero index these, then your y coordinate will be equal to your number modulo the height, and your x coordinate will be equal to your number divided by the height. So you can figure out what the x and y coordinate is, and then once you have the x and y coordinate, you can easily convert that x and y coordinate to a certain value. So here's what that looks like. You get the x and y coordinate, and then you print the x and y coordinate. This is just reading input. There you go. Okay, awesome. So that's problem A. Problem B, you have a string of x's and asterisks, and you need to replace some of the asterisks with x's. You always need to replace the first one and the last one, and you also need to replace a bunch more, possibly, so that you never have two x's that are farther than k apart. So the idea here is that you just keep looking at each of the asterisks, and if you ever see, okay, well, this asterisk is farther than k apart from the last x, that means there's an asterisk in the middle that you didn't replace with an x, but you need to replace it with an x. Because worst case, you're going to need something this or to the right to be an x, right? So if you do that, then you need to have the previous thing be an asterisk. So yeah, that's the idea. Let me draw that out a little bit better. Let's say you've got some x, you know the first character is going to be an x, and then you have like the last asterisk you placed was this. Let's do a star here. Now you're considering this element here. So if this range is more than k, let's say this is a range of k, we know you're going to have a problem here if you try and make this an x, if this was your last x, because it's bigger than k. You also know somewhere in this half of the array, after this character we're considering, you know there's going to be an x. Which means you know for sure this thing which used to be an asterisk, it should really be an x. So you can do this greedily. They guarantee in the problem that if you replace every star with an x, then you'll satisfy the requirements. So you know it's possible. So you can do it pretty easily like that. The code for that is, my code's a little messy, but you can definitely do it in a cleaner way. Yeah, so if there are no stars, then the answer is 0. I'm not sure if they guarantee this case won't come up, but it's just easy to special case anyway. And then you find the first and last star and the count of how many things you replace. If it's equal to the first star, or you need to replace the last thing, then replace the last thing. And then if it's equal to the last star and it's not equal to the first star, right, because you don't want to double count the first star, you need to replace the last thing with an x as well. Yeah. Yep. So yeah, that's solution to problem B. For problem C, if you've got so there's one key observation here. But the problem is you can delete from the beginning or end of two different strings. You want to know the fewest number of deletions required, so that after which you'll have, after like doing those deletions, you have two strings which are equal. So the observation here is that if you have some string, right, maybe you have like A, B, A, C, A, B, A, abacaba, classic example. If you delete a prefix and then a suffix, what you're left with is some continuous substring in the string. You can be left with any continuous substring in the string. So the problem we're trying to solve here is called longest common substring, I think, is LCS is usually what people abbreviate it as. But you want to find for two strings what's the longest string that they have in common of continuous characters. You can do this in n squared with a classic dynamic programming approach, but in this case bounds are so small you can literally just do the naive way of just like try every substring and then count with a for loop. So I is the index in the first string, j is the index in the second string, and k is the length of the amount we're trying to match. And I just say if there's ever a mismatch, then break out of this for loop. Otherwise, this is some possible match, so consider this. Finally, the answer at the end, right, if you have like 10 characters here, 8 characters here, and then 4 of them match, then you have to delete 8 minus 4 characters from this string, and you have to delete 10 minus 4 characters from this string. So in total, the characters you delete are going to be 8 plus 10 minus 4 times 2. Yeah, okay. So that's the answer there. Very good. On to problem D. Nope, that's E. Epic transformation. Yeah, this problem's pretty easy. So you can delete, if you have two different numbers, you can delete both of them. So the idea here is that what we can always do is take whichever element occurs most often, delete it with something else, right? So delete the element that occurs most often and second most often. The only time we'll be left with some array where we can't do anything is if we're stuck with some array that has all the same number, or just like an array of size 1, which technically is in the first category, but is easy to forget about. So if there are an odd number of elements, you know, best case scenario, you can get one element remaining. If they're an even number, you might be able to delete all of them, but there's a case in which you can't, which is if you have like 6 elements and 4 of them are the number 3, right? Then you can delete 3's twice, but you'll run out of elements that you can match up with a 3 in order to delete. So the idea for that is, this is like a common trick, but the only thing that matters is the frequency of the most common element. So if we know how many times the most common element appears, if it appears less than half the time, then we have a bunch of other things, right? And the approach we could use if they told us that we needed to actually do this is if the most common element appears twice, let's sort all of the elements by value. So we have 6 elements here, and we know the most common element appears 2 times. This is 5. Okay, that's 6. We know these 2 elements are the same. So what we could do is take each element and match it with the element that's 2 after it. So we can match these 2 together, we can match these 2 together. Well, I guess that's not strictly true. Yeah, that's not actually true. But we could match, yeah, so that's not the case. That's fake news. But what we can do is we can divide this in half. This is true. This is true news. Then we can match each thing with the thing that was n over 2 before it. Like that. There you go. There's your construction. That's the proof. So each element you can match with a thing that's halfway across. This will never break because we know at most some element occurs half of the time. So if it occurs for these 3 elements, then the thing this matches with is in the before the first half, right? So we subtract n over 2. That means in order for something to match with itself, you need n over 2. Like you need over half the array. Over half the array has to be that number. So yeah, there's your construction. Okay, so what if over half of the array is some number? Well, then that's pretty easy, right? So if we have 4 elements of one thing here and 3 elements here, every turn we want to delete something from this most common element. So we'll be able to make 3 deletions, 1 for each thing that isn't this most common element, and that'll delete 6 elements total, and we'll be left with the 1 element here. Right? If we had 5 of them, we could still delete 6 elements. So yeah, so you want the frequency of things that aren't the most common element. So basically, the TLDR of this is if we can delete 2 things that we want, anytime we have some element that isn't the most common element, that can delete 2 things. So the idea for how to solve the problem is we have a hash map for the number of occurrences of each element, and we store the most frequent element. So this is the count of the most frequent element. Then our answer is either the parity of the size of the initial array, so n mod 2, or we're allowed to subtract 2 elements for every element that isn't one of the max elements in the array. Whichever of those is bigger. Okay, that's problem D. Hopefully that made sense. 3 more to go. Problem E, restoring the permutation. So yeah, for this problem, if you think about it for a little bit, there's not really much you can do. Like, it might look hard in the beginning, but if you sit down and you think about it, you basically don't really have any choices. So let's look at this a little bit more slowly for a minute. So this first example is really quite good. 3, 3, 4, 4, and then 3 7s. So we have 3, 3, 4, 4, 7, 7, 7. Every time, like this first number, or every time we see an increase, we know that, well, first of all, how did we get this array? So initially we had some array, like maybe 3, 2, 4, 1, 7, 5, 6. Maybe this was our initial array. What we did was we look at each of the times we have a new maximum, and that would be these 3 cases. And then we kind of like propagate this to the right. So we have a 3 here and a 3 here, 4 here, 4 here, and then 3 7s. That's the approach we used to generate this initial array. Okay, so we know how to do that. Let's keep these circled because they're interesting. Why do we care? Well, like, yeah, we know every time there's a new element in this array, we know what it mapped to in the initial array. So the only things we have like choices for are these elements here. We also know which elements we have kind of like in the bank every time we want to replace some of these elements. So for this element here, we have all of the numbers that are less than 3. For this element here, we have all the numbers less than 4, which we haven't used yet. And for these elements here, we have all of the numbers less than 7, which we haven't used in any of the previous positions yet. So that's the idea, basically. If you want the minimum one, you just take the smallest element. If you want the maximum one, you just take the biggest element in the bank for each of these decisions. In that case, we have the operation of like add stuff to the bank, remove the smallest thing from the bank, and remove the biggest thing from the bank. Those are the 3 things we have to do. You can do all of those with a priority queue. So here is how you can do that. Hopefully this is big enough for you to be able to read the whole thing at once. We read in this array, we keep track of the minimum and maximum answer, and we make 2 priority queues, which we use to create the answer. So one of these is sorted by value, the other is sorted by negative value. Now, if you don't know how to do this, or you're using Java, where it's a bit messy to write this, I guess it's not that messy, but yeah, whatever. Like, maybe there are different ways of doing it. What you can do is, instead of writing a different comparator, if you want to, you can just add the negative version of the number to the priority queue. So then it'll still be sorted in increasing order, but it'll be sorted in decreasing order, which is what you want if you imagine everything as being negative when it's inside the priority queue. So that's one trick. In C++, priority queues are the opposite of what they are in Kotlin and Java. They pull the biggest things out first rather than the smallest. So there's a gotcha if you're new to that. Otherwise, yeah, it's pretty straightforward. So this just checks whether it's a new element, if it's the new biggest thing we've seen, and then we add all of the stuff smaller than it if it is, and then if it's new, it's forced. It has to be AI. If it's not new, then we just take either the biggest or the smallest thing that we want. This will remove it from the priority queue, and then we put it in this position in the array. And then we print our answer at the end. Cool, it's problem E. Two more problems. Problem F. Yeah, so this problem was a little bit messy. If you draw out what it looks like, it winds up being not too bad. So I'll draw out like the general approach, and then, yeah. So what the triangle looks like is you have a bunch of edges like this, and then like a long continuous range like this. So you've got like streaks that look like this. So you want to know how many times would you go like against the flow if you needed to get to some position. I think it's easier if you consider yourself on one of these edges. You can go right for free as much as you want. So what I do is like, I imagine, you know, you can get to the next position you're interested in. So I imagine just going here for free, and then every time you move left, you're like, okay, well, moving left has a cost of 1, right? Because you don't actually move left now, you move left earlier, but like, let's say you wanted to move left here, you'd pay this left cost here, and then you could take this, or then you would take, it doesn't look like this, these circles are wrong. Let me try again. It looks like this. Okay, so let's say you're at this position. You want to get to this position. What you would say is you end up here for free, but you can move left 2 times for a cost of 1. And you don't pay the cost of 1 at the end. You would pay the cost of 1, I guess, in the beginning, right? Or like as you need to. So you could pay your cost of 1 to move left here. There's 1 cost. You end up here now. Maybe instead of this position at the end, maybe you want to end up here, for instance. So in this case, you would pay your cost of 1 at the beginning, and then you move 2 spaces here, and then you can move another 2 spaces for free, but you only want to move 1 of the 2 spaces, so you pay your cost of 1 here instead. So yeah, if you start at one of these like horizontal lines, then it's very easy to solve. If you start at one of the other lines like this, it's also still pretty easy, because here's the idea. If you need to go right the entire time, then the cost you have to pay is pretty easy to figure out, right? You just, like, you have to go right the entire time, so you just math it out. Otherwise, you're gonna go left sometime. You might as well go left now, because it doesn't really matter. So you go left now, and now you're on the easy case. So you just call your function that handles the easy case, and you're good. The code for that looks like this. So here's the cost from going from one square to the other square. Now, you can also figure out the order you'll hit these squares pretty easily by just sorting them by row, because you can only move down, so obviously you have to hit the smaller rows first. So you can pause this if you're interested in what the actual code looks like, but that's the general idea for the logic. And then finally, we've got one more problem left, which is problem G, maximize the remaining string. And yeah, in this problem, you can pick some character, or if you have 2 of some character, you can delete 1 of them, right? So you want to delete as many characters as possible. After doing that, you want, after deleting as many characters as possible, you want the string to be lexicographically maximal. So in other words, you want the first character in the string to be as big as possible. After doing that, you want the second character in the string to be as big as possible, and so on, all the way till the end. But the priority is the first character over everything else. What we can do is just say, let's imagine the first character was a Z. Then we'll ask, is it possible to create a string if the first character is a Z? So we do that for the first character. If it is possible with a Z, then we're like, okay, we're gonna pick the first Z, we're going to make that the first character, which means we can't pick anything before the first Z. We also aren't allowed to pick any other Z's in the entire array, or Z's, I guess, maybe if you're Canadian or European or something. So yeah, that's the idea. If we can't pick a Z, we try Y, then we try X, then we try V, W. Wait, what? Never mind. Who knows the alphabet? Too difficult. What comes before X? W, surely. W, X, yeah, W. W, X, Y, Z. So yeah, so we do it in that order. The code for that is pretty simple. So okay, let's see like, what is the check to see is it possible to do this? So what I do is I say, this is pretty messy and like very difficult to read if you don't know Kotlin. So maybe doing it in Kotlin isn't a great idea, but oh well. It was fun. I had fun. So we're gonna say if this is the string and the first character you take is this, then return a bit mask of the characters you end up taking, which is just basically a binary number, where in binary it has a 1 here on this position if you take this number, or a 0 if you don't. So the idea is I go through each of the elements, and I'm not allowed to take anything before whatever this first character I take is. So if I haven't seen one of these characters, then I just skip this element. Otherwise, I put a 1 in this position. So binary OR will like put a 1 in this position if there isn't one. And then the thing I want to OR it with is a 1 with the number of zeros after being whatever position this element is in the alphabet. So the important thing here is if the bit mask ends up changing, then that means that I can't make this element the first thing I place, right? If the string is ABC, if C is the first thing you place, then you're not going to be able to place an A and a B. And that's bad, right? But if the string is ABCBA, then you can place a C first because you're still able to place B and A. So I brute force what the first thing I take is from Z to A. If I can take it, then I do. And then me taking it requires a little bit of maintenance, but it's still pretty easy. In particular, what I have to maintain is I can't take anything before that. So I delete that from substring. I also can't take any more of these characters, so I replace the substring with these. And then it's possible that like I first place an A, and then I place a Z, and then I place a Y, right? So this has to get pushed back into the alphabet later on. The last part, which is a bit messy, I guess, is this part right here. I remove it from my mask. So there aren't any more characters in the string, and I have to say now not changing means you are still able to place every character other than the ones you've already placed. So that's kind of a minor modification. And that's the solution to problem G. All right, so that's all the problems in the contest. This video is going to be way longer than it should because it's a div 3 round. It should be like 20 minutes, but you know, as it stands, I'm not geothermal. So it takes me more than 20 minutes to do this set. Also, problem B took me like 20 minutes on its own. That was an embarrassment. Anyway, I hope your rating went up if you did this contest. I hope you enjoyed it. I thought the problems were pretty good. I wasn't a huge fan of them, but I thought they were decent. So yeah, thanks for watching. Have a great day, and don't forget to do CodeGym qualification round.